Okay, so we're going to get the fundamental theorem of calculus part 2 now. Oh, I didn't turn the camera on, so that's... Try that again. Recording. Okay. If you're going to watch the recording later, the first minute or so is dead time. There we go. Okay, we really don't have that many sections left. I'm going to do 5.3 now. 5.4 is not really that much of a new section. It's kind of a combination of 4.9, believe it or not, and 5.3. Okay, so 5.5 is the last real new material, so to speak, after I do fundamental theorem of calculus part 2. Okay. All right, so show you fundamental theorem of calculus part 2. And then after I've done enough, I'll stop and let you ask questions. And so we may finish early. We'll see how it goes. Okay, so fundamental theorem of calculus part 2, page 396. Okay, here it is. It's correct. You can use the version that's here. I will show you a derivation of it. And I'll just say something quickly about this. Okay, fundamental theorem of calculus part 2, you prove it with FTC1. And then after that, FTC1 becomes almost lost, but it gets dropped by the wayside. You'll be doing FTC2, well, the rest of our course, you'll be doing FTC2 Calc 2. Those of you going on to Calc 3, you'll do FTC2. You're almost never going to do Part 1 anymore, to be honest with you. Okay, but fundamental theorem of calculus Part 2 owes its existence to fundamental theorem of calculus Part 1. Okay, so it uses Part 1. Then after that, you just don't use Part 1 anymore, hardly. Okay, so you really want to know this theorem for sure. It's pretty easy, to be honest with you. Okay, so FTC2, I'll show that to you. You'll use it for Calc 2. You'll use it for Calc 3. You use it for differential equations. However high up, you really want to know this theorem. So I'll go over a derivation of it. Okay, so I'm not even showing you what it is yet until I show you a derivation. But the derivation is based on fundamental theorem of calculus part 1. And I'll just quickly add this. So Calc 1 teachers always do a mean trick on students, 2 parts. Okay, so first mean trick that Calc 1 teachers always do is first you do the derivative by the definition, right? And you'll still need to have that for the final exam. You know, limit h approaches 0, f of x plus h minus f of x all over h. Okay, we make you guys do all that. A real mean trick. And then after that, we show you the shortcuts, right? So most of the rest of the semester, we did shortcuts. Okay, we're doing the exact same thing right now with integrals. Okay, so first we did section 5.1, 5.2. The mean trick was we estimated the definite integral, like a definite integral from A to B, and we did chop, 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 right? Take left endpoints, right endpoints, midpoints. It was really tedious. Get out your calculator. And you don't even get the exact answer, right? It was only an approximation. Okay. So that's the equivalent of what we did when we make you guys do the derivative by the definition, limit h approaches 0, f of x plus h minus f of x all over h. You say, man, this gets really tedious. I wish there was a shortcut. Okay. And then here's a shortcut, right? Oh, good. Now I can just do the shortcut. Same thing is happening right now. So I did a mean trick on you, made you do areas under a curve by chopping it up into a whole bunch of pieces, right? Finding left sums, right sums, and using midpoints, and it wasn't the exact answer. Now we're doing a shortcut, and we're giving you the exact answer. Okay. All right, so I'm going to go over the derivation. You are not responsible for the derivation. Okay. I am responsible for the derivation. So frankly, if you don't even want to pay attention for about 5 minutes, you don't have to. But some of you might be interested. You know, where does this theorem come from? How did it come about? So here it is. So I'll tell you when you can pay attention again. So if you want to, frankly, if you want to take a 3 or 4 minute nap, you can right now, because I'm not testing you on this material. Okay, how do you like that? A teacher actually tells you, you know, when you're allowed to take a nap and when you can't. But anyway, but somebody says, you know, where did this theorem come from? So the easy way out for me is just say, here's the theorem, use it, right? But I'm responsible. I'm supposed to show you, here's where it comes from. This is why it works. You might not follow it all, but that's okay. All right, so here's the derivation of FTC2. So from FTC1, we have this. If g of x is the integral from a to x of f of t dt, with f is continuous, we said before constant here, variable here, then g prime of x is equal to f of x, right? And all you do for the derivative is put x right there. Okay. All right, so that means by definition, g is an antiderivative of little f, right? Here we're taking the derivative, so we go the other way, g is considered an antiderivative by definition from 4.9, right? Okay, now suppose capital F is any antiderivative of little f. That'll be a key point later on. Okay, capital F is any antiderivative. We already know it exists because we already have one antiderivative, g. G is an antiderivative of f because g prime is equal to f. Okay, so let capital F be any antiderivative. That means g and f differ by a constant, okay, from section 4.9. If g of x is an antiderivative, and if capital F is also an antiderivative, they differ just by a constant. That means g of x is equal to capital F of x plus c. All right, remember in 4.9, we had a whole class of antiderivatives, but they were all the same except for a constant. Okay, so here, g is an antiderivative. Capital F is any antiderivative. That means they differ by a constant. G of x is equal to capital F of x plus some constant. Now I'm going to plug in a. G of a equals capital F of a plus c. Okay, but what is g of a? Okay, so looking back over here, if I plug in a right there, then I'm taking the integral from a to a. Well, we know the integral from a to a is always 0. G of a is 0. So I plug in 0 right here in place of g of a. 0 equals f of a plus c. That means c is equal to negative f of a. Okay, a little bit of algebra, subtract that over. C is negative f of a. I found c. I'm going to put that back right over there, which means g of x is f of x minus f of a. I figured out what the constant was. Now I'm going to plug in x equals b. Put a b right there, put a b right there. G of b is capital F of b minus capital F of a. G of b, by definition, means put a b right there. So G of b is the integral from a to b of f of t dt. That's capital F of b minus capital F of a. Okay, and I sort of have it, but now that I don't have x anymore, I don't have x here or here, it's just a constant. Instead of f of t dt, let's write it the way we normally do, f of x dx. So this is the final result. Integral from a to b of f of x dx is capital F of b minus capital F of a. And this is FTC2, fundamental theorem of calculus, part 2. Okay, so this was the derivation. This is the result. Okay, so everybody has to wake up again. So pay attention once more. Okay, now if you say to yourself, I did not understand anything you did over here, that's okay. Somebody might have gotten it. It's my responsibility to show you where it came from. What are you responsible for? Just being able to use the theorem. Okay, so we finally tie everything together. There's FTC2. The definite integral from a to b of f of x dx is capital F of b minus capital F of a. Okay, so finally we tied together 4.9 and 5.1 and 5.2. Okay, remember I showed you the symbol for integration. We were doing indefinite integrals. Indefinite integral means don't put a number here, right? It was just integral symbol, f of x. So we integrated capital F of x, let's say, plus c. Then when we got to 5.1, 5.2, we used the same symbol, and we said it represents an area under the curve. And said that doesn't make sense. You know, we're using the same symbol for two different things. Actually, it isn't. Now we're finally putting it all together. So what does all of this mean? Okay. So we go ahead and take an antiderivative, okay, just as we thought. And since capital F is any antiderivative, the easiest one is where the c is equal to 0. So normally when we do these so-called definite integrals, when you integrate, don't put the plus c. You plug in the b, you plug in the a, and then you subtract. Okay, so that's the result. Put this on your cheat sheet. Go ahead and put this on your cheat sheet. In fact, the book gives a nice little summary of both of the fundamental theorems of calculus. So maybe the best I could say for you on page 398 is to put both of these in. So here's fundamental theorem of calculus, FTC 1 and 2. Suppose f is a continuous function on AB. Here's FTC 1. If g of x is the integral from a to x of f of t dt, then g prime of x is f of x. Okay, constant here, variable here. Frankly, you're not going to use this hardly at all in Calc 2 and Calc 3, for those of you going on to Calc 2 and 3. You're going to use this much, much more. Okay, so part 2, the definite integral from a to b of f of x dx. Okay. So we did definite integrals in sections 1 and 2, right? We took the picture, chop, 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 chop it up into so many pieces, right? Pick the left endpoints, right endpoints, midpoints, you know, do base times height, all that stuff, and we were only getting an approximation. Right? Now we're daring to say by this theorem, you don't even have to draw the picture. You're not chopping it up into so many pieces. Okay, just integrate, plug in the top number, plug in the bottom number, and that's the exact value of the integral. Not an approximation, not off by a little bit. Okay, it's the exact value of the integral by fundamental theorem of calculus part 2. Very nice theorem. Now, the theorem that we stated, and that was one of the key points, was let capital F be any antiderivative, of which there are infinitely many. Okay, so whatever the antiderivative is, you can do capital F of B minus capital F of A. So since we can pick any antiderivative, the easiest one to pick is where the C is 0, right? So from section 4.9, when we integrated, it was always blah, blah, blah plus C, correct? So let's say the integral of x squared dx was x cubed over 3 plus C, right? Or the integral of cosine x dx is sine x plus C. C can be any real number. Since the theorem says capital F can be any antiderivative, for this section, since we can pick any antiderivative, the easiest antiderivative is if C is 0. Okay. So normally you don't need the plus C for FTC2, for definite integrals. Okay. So for indefinite integrals, so what is indefinite integrals? That was 4.9. That was when there was no number here and here, right? The answer was blah, blah, blah plus C. You have to put the plus C. Now you don't put the plus C because the theorem says you can pick any antiderivative. So the easiest antiderivative is where the C is 0. So for these definite integrals, we still integrate. Again, what is integrate? Anti-differentiate. Okay. You plug in the top number, plug in the bottom number, and that will be the exact answer. Not approximation. You don't have to draw a picture. You don't need to chop, chop, chop into 5 pieces or 6 pieces. You don't need to pick the left endpoint, right endpoint, midpoint. Okay. Just integrate, plug in. That'll be the exact answer. Okay, so I was going to do some right now. And there we go. So starting with problem 19 until the rest of the assignment, it's FTC2, Fundamental Theorem of Calculus, Part 2. So I guess 19 through 41. Okay, so I'll do some. And then when I'm done, I'm finished for the day. I'll probably need maybe 10, 15 minutes to do that. And then you may ask questions, but if not, we can just stop. Okay, since I think we're very much ahead time-wise. And like I said, even for section 5.4, it's not really that much of a new section. There's hardly any new stuff in 5.4. Okay. All right, so let's take a look. For 19 up to 41, these are definite integrals. Right? That means there's a number here and number here. Okay. Section 5.1 and 5.2, you had to maybe draw a picture, chop it up into so many pieces, right? Draw a rectangle. You don't need to do any of that. Okay, so we were basically doing a mean trick on you. Okay. It's sort of like we were doing a mean trick on you for doing the derivatives by the limit definition, and then after that we show you the shortcut, right? But it's always that way for Calc 1 students. You do the long cut and then you appreciate the shortcut. So we're doing the same thing for the integrals. You did the long cut by doing, chop it up into so many pieces. Say, man, this is sure tedious, right? And left endpoints, right endpoints, midpoints, and then you appreciate the shortcut. Okay. All right, so I'll do some of these, and you notice how fast the answer comes out. Okay. I'm not drawing the picture. Don't need it. I'm not chopping it up into 10 pieces or 8 pieces or whatever. I'm not taking the left endpoints, right endpoints, midpoints, punching it in my calculator, and only getting an approximation. Okay. I will integrate, and I'll get the exact answer. Very powerful. Okay, integral from 1 to 3, x squared plus 2x minus 4. Okay, x squared, x cubed over 3. Integral of 2x is x squared. Integral of negative 4 is negative 4x. Notice, don't put the plus c now. When do I put the plus c? Indefinite integrals. Okay, definite integrals, don't need to put it. But again, you can still check. How can you check your integration? Take the derivative. The derivative of this, x squared. What's the derivative of x squared? 2x. What's the derivative of negative 4x? Negative 4. It definitely works. Notation. Okay, and I want you to do the same thing. This funny looking s that's on the left, it somehow migrates to the right side and straightens out. That's considered standard notation. I mean, I think it's dumb, but that's the way it is. So it starts off on the left, it comes to the right side now, and it straightens out. So just draw a straight line, 1 to 3. Okay. Then in parentheses, plug in 3, minus parentheses, plug in 1. Okay, so put a 3 right here. 3 cubed is 27. 27 divided by 3 is 9. Plus 3 squared, which is 9. Minus 4 times 3, which is 12. Here you plug in 3. Minus parentheses, plug in 1. 1/3 plus 1 minus 4. Grind it out. That is the exact value of this integral. Not close, not maybe. No picture. I didn't draw a picture. I didn't draw any rectangles. This is the exact answer. Okay, so let's see. 9 plus 9, 18 minus 12 is 6. Then I distribute it. Minus 1/3, minus 1, plus 4. 6 plus 4 is 10. Minus 1 is 9. So it's 9 minus 1/3. 9 minus 1/3 is 8 2/3. So I just leave it as 8 2/3. Okay. And furthermore, the theorem states this is the exact answer, not approximately. The exact answer. Pretty nice theorem, right? Okay, so you definitely want to know this theorem. You're going to be using it in Calc 2. You're going to be using it in Calc 3. All right, so I'll do several more of these, and that's as much as I was going to do today. So 23, integral from 1 to 9 of radical x dx. Okay. So treat this as x to the 1/2, integral from 1 to 9. Okay, power root, x to the 1/2, x to the 3/2, and you should know this game by now, divided by 3/2, right? Divide by 3/2 means times 2/3. Don't put the plus c. Funny looking s straightens out, comes to the right side from 1 to 9. That's the proper way you write calculus. So if you don't write it correctly, I can still take up points. Okay, you have to write mathematics properly. So it starts off with a funny s on the left side. It migrates to the right side for some reason from 1 to 9. I guess if it moves from the left to the right, it's almost as if to say, okay, you know what you're doing. If you intentionally put it on the left side here and you put it on the right side here, you know what it means. And now I plug in 9, I plug in 1, and I subtract. Okay, by the way, you're allowed to factor out any constant. So take the 2/3 out. Okay, 9 to the 3/2 minus 1 to the 3/2. Okay, so constant 2/3 comes out. Technically, you don't have to do that, but it makes it a little bit easier. So take the 2/3 out, right? And then plug in 9, 9 to the 3/2, subtract 1 to the 3/2. Well, you know 1 to anything is 1. Okay. 9 to the 3/2 powers, the 2 means the root. So square root of 9, 3. 3 cubed, 27. 27 minus 1 is 26. 26 times 2 over 3, 52 over 3 is the answer. The exact answer, not an approximate answer, like if we chop, 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 right? The left endpoint, right endpoint, midpoint, we would only get an approximation. This is the exact answer. Okay. So that's what, 17 1/3? Okay. So the problem's finished, but I'll dig deeper. A little sidebar here. We know this is what square root function looks like, right? Y equals square root of x from 1 to 9. like that. This is 1, comma 1. This is 9, comma 3, right? That area, the exact value is 17 1/3. Okay. It's actually pretty amazing that we can come up with an exact answer for curved objects, right? So before we said, you know, we only know how to find areas if they're straight lines, right? Like I can do rectangles, triangles, trapezoids, squares, and circles or parts of circles, because I know the formula for the area of a circle. But what if I have a curve? Okay, before we said we couldn't do it. Now we can do it. Okay, under the curve of y equals square root of x, believe it or not, between 1 and 9 is exactly 52/3, 17 1/3. Not approximately, exactly. Okay. All right, so I'll do a few more. I was going to do 31, 39, 33, and 37, actually. Okay, and then I'll be done. And then if you want to ask questions, you may. Okay, integral 31, pi over 6 to pi over 2, cosecant t, cotangent t, dt. Okay, what's the integral of cosecant cotangent? It's negative cosecant of t. Okay, so recall that the derivative of cosecant t is negative cosecant cotangent, which means the integral of positive cosecant t cotangent t is negative cosecant t. Okay. All right, I like to play this trick. You know that there's going to be subtraction, right? There's going to be a minus and a minus. Okay. What did I do from here to here to make it easier on me? One less negative symbol. I changed a negative to a positive, and look at what I did with the limits. I switched it. Okay. It just prevents me from having to do a double negative. Right? There's a negative. I plug that in, minus, and then there'll be another negative maybe. Right? So if you ever want to avoid a negative, make it a positive and switch these two around. We know that trick, right? So it's positive cosecant t, and then pi over 6 goes on top, and pi over 2 goes on the bottom. Right? So we've mentioned that theorem before. I'll show that to you again one more time for emphasis. Some of you might think it's an overemphasis, but that's okay. It's back on 5.2, page 385. Right there, right? Integral from b to a is the negative of the integral from a to b, right? Integral from b to a, integral from a to b are opposites, okay? Which means if I don't like integrating something that has a negative, I'll just make it a positive and switch these two around. All right, plug in the top, cosecant pi over 6, minus plug in the bottom, pi over 2. Okay, cosecant is the reciprocal of the sine. Right? So I take the sine of each of these and flip it. Okay, sine of pi over 6, sine of 30 degrees is a half. Okay, so sine of 30 degrees, sine of pi over 6 is a half. Flip 1/2, you get 2. Okay, for cosecant pi over 2, sine of pi over 2 is 1. Flip it, reciprocal of 1 is 1. So 2 minus 1, 1. So the answer is just 1. So there we go. Okay, 39. 8 over 1 plus x squared dx. Okay, 1 over radical 3 to radical 3. Okay, 8 is 8 times 1, right? So I want to think of it as 1 over 1 plus x squared, because 1 over 1 plus x squared is my hopefully familiar inverse tangent. Okay, so take the 8 outside. You're allowed to do that. So that circle and that arrow there means I'm taking the 8 outside. I have 8 times 1 over 1 plus x squared. Right? Remember, the derivative of inverse tangent is 1 over 1 plus x squared. Therefore, the antiderivative of 1 over 1 plus x squared is inverse tangent. Okay, don't need the plus c from radical 3, 1 over radical 3 to radical 3. Okay, so take out the 8. Inverse tangent, upper limit, radical 3. Inverse tangent, 1 over radical 3. Okay, this involves a little trick. If you already have it memorized, great. This turns out to be pi over 3. This one here. This one turns out to be pi over 6. Okay, so the answer turns out to be 8 pi over 6 or 4 pi over 3. Okay, I'll take a little extra moment to talk about this a little bit more. Okay, but this is pi over 3. For now, just take my word for it. This is pi over 6, and I'll talk about a trick to getting that. Okay, so that's 2 pi over 6 minus pi over 6 is pi over 6. So I have 8 pi over 6, 4 pi over 3. Okay, but let me digress a moment and show you the trig involved for inverse tangent of radical 3. Okay, so let me make this disappear. I think I may have shown this to you before, but I'm sure so. Okay, so I'll call it x. Okay, unscramble it, write it without the -1. Tangent of x is radical 3, which I'm going to write as radical 3 over 1. Tangent is sine over cosine. Like that. Okay. And then the trick you do from here is divide top and bottom by 2. Go like that. Why? Because it works. Okay, so then I just equate these two. So that means sine x is radical 3 over 2, and cosine x is a half. They're both true. Okay, so what first quadrant angle is like that? Well, cosine x coordinate is a half. I go like that. Okay, so that looks like it's 60 degrees. So that's how I got pi over 3. Okay, and you play that same trick for this one, and you get pi over 6. Okay, and I have time. I'll go ahead and show you that one. So that tells me inverse tangent of radical 3 was pi over 3. That's how I went from here to here. Okay, and same trick for this one. Inverse tangent of 1 over radical 3. So scratch paper here. Again, call it x. Unscramble it. Get rid of the -1. This says the same thing as a tangent. See, are you taking the tangent of this? No, you're taking the tangent, inverse tangent of 1 over radical 3. You must be taking the tangent of something else. The only else there is x. 1 over radical 3. Okay. Right tangent is sine over cosine. Sine x over cosine x equals 1 over radical 3. And then now you play the same trick. Divide top and bottom by 2, like that. And why do I do it? Because it works. Okay. So that means sine of x is a half, and at the same time, cosine of x is radical 3 over 2. Well, they're always paired like that anyway. Okay, so this time I want the y coordinate to be a half. Go like that. So that looks like 30 degrees. This is radical 3 over 2, comma 1/2. So the cosine of the angle is radical 3 over 2. Sine of the angle is 1/2. So that looks like it's 30 degrees, or pi over 6. So that leads me to this conclusion. Inverse tangent of 1 over radical 3 is pi over 6. Okay, so that's the finish of that one. Okay, then the next one I want to show you is 33. Yeah, I'm going out of order intentionally for a reason, but 1 plus r cubed dr. I'm going to go from 0 to 1. Okay, what is the derivative of 1 plus r with respect to r? 1. Okay, I don't have to worry about the chain root, which means I'll just do the power root. I don't have to multiply this out. Okay. Yes, you can multiply 1 plus r times 1 plus r times 1 plus r, and you get all the, what is it, r cubed plus 3r squared plus 3r plus 1, something like that. Okay, no, just do the power root. So 1 plus r to the 4th power over 4, from 0 to 1. And again, what answers all questions is, what's the derivative of this guy, right? If you take the derivative of this, 4 comes down, knocks out that 4. It would be 1 plus r cubed, there it is, times, by the chain root, the derivative of the inside. But the derivative inside is 1, so it works. Okay. Now, let me hasten to add, if this had been an r squared, 1 plus r squared cubed, the only way to do this one would be to multiply it all out, because the chain root would not work in that situation. Okay, so if you try to do the power root, you'd fail there. Okay, but in this particular case, no issues. All right, so I plug in 1, 2 to the 4th over 4. Plug in 0, 1 to the 4th over 4. Okay. Don't need the plus c. The funny looking s migrates to the right side, straightens out. Plug in the upper limit, plug in the lower limit, subtract. 16 minus 1, answer is 15 over 4. Okay, and the last one I was going to show you was 37. And what time is it? 15 to. Okay, x to the e to the x. Okay, so just see that you can tell the difference between the two. Aim it right. Yeah, I can get it to focus better if I raise it up, but unfortunately I can't hold it. I'm not sure you can see what I'm doing, but I'm holding the book up so I can't write now. Okay, what's the integral of e to the x? E to the x. X to the e, you use the power rule. That's like x to the 2.718, blah, blah, blah. You do it just like x squared or x cubed and so on. Okay, I'm putting the book down because it's heavy. Okay, so I'll be done in a couple of minutes, folks. So if you want to ask me questions or put it in the chat, you may. But otherwise, we can finish early. I don't mind. I'm guessing a lot of you don't mind either. Okay, integral of x to the e plus e to the x. Notice there's no picture. I don't know what this graph looks like. I know what that looks like. I know a little bit about that, but when you add them, it's a little bit tough. But whatever it looks like, between 0 and 1, we're finding the exact area under the curve, believe it or not. Okay, integral of x to the e is x to the e plus 1 over e plus 1. Okay. Yeah, that's like 2.7 plus 1, 3.7. But yeah, leave your exact answers. Leave e as e, right? Leave square roots as square roots. Leave ln as ln, unless directed otherwise. And what's the integral of e to the x? E to the x. Don't need a plus c. 0 and 1 move over to the right side. Okay, plug in 1 in parentheses. Plug in 0 in parentheses. Okay, so 1 to the e plus 1. Well, 1 to anything is 1. So that's 1 over e plus 1 plus e to the 1. But what's e to the 1? Just e. Minus parentheses. Don't forget the parentheses. You need parentheses here. Okay, plug in 0. Well, 0 raised to anything is 0. Plus e to the 0, but e to the 0 is just 1. So all of this is saying I'm subtracting 1. So final answer, 1 over e plus 1 plus e minus 1. And that's it. We're done. Okay, so I'm actually finished. So if you have a question, you can ask me or put it in the chat or unmute yourselves. Otherwise, we're going to be done. Let me just show you where I'm headed. So I was finished with section 5.3. So and we've got so much time, okay? Unless, of course, my internet goes down, then you know what to do. Okay, so you should know by now, if my internet goes down, hang in there. I'll be back eventually. Okay, so I can mark this off. The test is until next Thursday. I only have 2 more sections. And I'll mention something quickly about 5.4. Let me show you what 5.4 is. So look at question 5 and 6. Those are indefinite integrals, right? 7, 8, 9, 10. Those are indefinite integrals, meaning there's no number here or here. It's just like 4.9. You integrate, your answer is going to be blah, blah, blah plus c. And look at what happens starting with 21. Definite integrals. So your answer is not blah, blah, blah plus c. It's going to be a real number. You don't put the plus c. You still integrate, plug in the upper number, plug in the bottom number, and your final answer will be a real number. Okay. Now, that's not completely all there is to this section, and there are some word problems at the end, but the majority of the section is stuff like that. Okay, so now that I'm done, let me go check the chat. I do know some of you put something in the chat. So let me see what that is. Okay, got somebody asking for 5.3, 21, and 29. Okay, so let me see what that's about. 5.3, 21, and 29. Okay. 5.3, 21. and 29. Five point 321. Integral from 0 to, move the chat out now, 4/5 t cubed minus 3/4 t squared plus 2/5 t dt. Whoops. All right, doesn't look too bad. So 4/5 t to the 4th over 4 minus 3/4 t cubed over 3 plus 2/5 t squared over 2. Don't need the plus c. 0 and 2 migrate to the right side. Okay, so clean this up. 4's cancel out, 3's cancel out, 2's cancel out. It's very nice. So it's 1/5 t to the 4th minus 1/4 t cubed plus 1/5 t squared from 0 to 2, looks like. Plug in 2, plug in 0. Oh, plugging in 0 is very easy, right? 0, 0, 0. You see that theme quite a bit when we do more of these. Quite often when you plug in 0, you get 0, right? What's 0 to the 4th? 0. 0 cubed is 0. 0 squared is 0. Multiplied by whatever, it's 0. Add them all, it's 0. Okay, so 2. 2 to the 4th is 16. 16 over 5. And 2 cubed is 8. 8 divided by 4 is 2. And plus 4 over 5, looks like. Okay, so 16 over 5 plus 4 over 5 is 20 over 5, that's 4. 4 minus 2 is 2. I believe the answer is 2, right? These two combined is 4, right? 20 over 5. 4 minus 2 is 2. Okay, and then 29 was asked for. Integral from 1 to 4, 2 plus x squared over radical x dx. Okay, there's no such thing as a product rule for integrals. There's no such thing as a quotient rule. So we have to do something else. So in this case, there's something else is just divide them out. Okay. Okay, 2 over radical x is 2x to the negative a half. X squared over x to the 1/2 is x to the 3/2. Right? 2 over x to the half, 2x to the 1 negative half. This is x to the 2 divided by x to the 1/2. 2 minus a half is 3/2. Okay. So 2 x to the 1/2 divided by a half. There, divided by half. X to the 5/2 divided by 5/2. Can you guess what I'm going to write? Times 2/5. Don't need the plus c. Go from 1 to 4. 4 root x plus 2/5 x to the 5/2. 1 to 4. Paren, paren, minus paren, paren. Here you plug in 4. Upper limit. Here you plug in 1. Lower limit. Okay, so 4 times the square root of 4. 4 times 2 is 8. plus 2/5, 4 to the 5 halves. Plug in 1, 4 times 1 is 4. 1 raised to anything is 1, so plus 2/5. Okay, let's see. 4 to the 5 halves means square root of 4, 2. 2 to the 5th power is 32. So I'm claiming this is the same as 32. Okay, if I did that right. 4, 2, yeah. And plug in 1, 4 plus 2/5. Okay. So what do I end up with? 8 plus 2 times 32 is 64 over 5 minus 4 minus 2 over 5. So 8 minus 4 is 4 plus 62 over 5, which is 20 over 5 plus 62 over 5. So 82 over 5. That's going to be my final answer, I believe. Okay. All right, that's about it, folks. Let me check. I think I've caught up with the chat. Yes, I've caught up with the chat. So anything else? Otherwise, we can call it a day, folks. Yeah, you can ask more questions tomorrow, but tomorrow I'll get started with 5.4. And we only have 2 sections left, so we have plenty of time. Okay, I don't see or hear anything else, so I guess that'll be it. All right, that's it for today, folks. So everybody have a good afternoon, and we'll see you tomorrow. Okay, bye, everybody.